Okay, so good morning, everyone. The idea for today is to work with Matlab, Topotools, and enhance our understanding of the calculation of steepness indices, chi indices, and quantitatively analyze tectonically active landscapes. Before we dive in our interactive Matlab session, I just wanted to point out that last night I've been updating the web page, and I've been adding links to the individual sessions, and I've also been updating some of the Python and Jupyter notebooks and turning them into PDFs. So these are resources you can use, you can access, and specifically maybe tomorrow or later today, we may be looking at a modeling exercise where I show how you can use a real digital elevation model, for example, from the Baspa Valley in the northwestern Himalaya, and forward model it using the stream power erosion approach. Okay, having said that, yesterday we generated a digital elevation model, a 1 meter digital elevation model from the Santa Cruz Island, right? There was a point cloud that we have had. We did the PDAL exercise. We classified the point cloud, and then we gridded it to a digital elevation model. So that is a very typical approach that you do when you have a LiDAR DEM or a structure from motion DEM. So that will be the steps that you do to generate a high-resolution digital elevation model. So the idea for today is use that DEM, at least in the morning session, and perform analysis on it, derive steepness indices, calculate slopes, and so on and so on. I was able to reduce the size of the DEM. If you go into the folder Matlab Topotools, you will see a file that is roughly 27 megabytes large. I can make this larger, hold on. And it is called POSO USGS. POSO is the name of the catchment on the Santa Cruz Island, so this is why it's called POSO. It's an old Native American name. What is the dog doing? It's an old Native American name. The USGS is the United States Geological Service because they produced the data, so they have flown the airplane. And it is in UTM 11 coordinates, and I've been using the NAD 83 datum, which is related to the WGS 84. And this is a 1 meter DEM. So one of the reasons why this DEM was so large yesterday, you remember it was more than 100 megabytes when we generated it. The reason for that was it was saved as a very high precision floating DEM. It was saved as a so-called float 64 file. So it had a 64-bit float integer, which means that it has a precision that would go up into the micrometer environment. So in other words, with that numbers of values that we have for each grid cells, we can store micrometer precision, and that is totally overkill. You know, we maybe have a centimeter precision. So I converted that to a float 32, and I compressed it, and now it is in a good format. So please download this. We will be using this. I also have a couple of PDFs on there that may be instructive for one or the other things. If you would like to hear more about the Santa Cruz Island, then the El Nili publication is useful. That is a former master student from Santa Barbara with whom I worked on that island for a long time. Fiona Clubb was a recent postdoc at Potsdam. She is now a professor in Durham, and she and we have worked on river profile clustering for that island. So these are additional information. We will not cover all of those things in detail. I'm just pointing out, if you're interested, you can dive in there. We also provide the theoretical background in some of those papers. And then, of course, Wolfgang Schwanghardt's explanation of Topotoolbox. So he is a programmer of Topotoolbox. He has been developing this over many, many years, and it is a very useful resource for doing quantitative analysis. I also put a quick and dirty Matlab file on it, which is called Topotools First Steps. I put that on there so that you can follow along. You can download this as well, and we will open it in the Matlab editor. But you likely would want to add comments. So this is not a finalized file. This is a file that we will work on. It's just a guidance for you to see where we are. Because sometimes the command gets a little longer, so instead of you typing several lines of code, you can use this. But I want you to comment this file. It doesn't help you anything if you just copy and paste the commands, right? So you need to be able to perform some of the analysis yourself as well. Okay, let's dive into Matlab Topotoolbox, and I will be explaining some things along the lines, for example, how the stream power law works and how we can use log area, log slope plots for deriving steepness indices. I make the assumption that everybody has Matlab running or is able to run Matlab on their laptops, right? And I think most of you have worked with Matlab before. Who has not worked with Matlab? But you have a Python understanding somehow? There are many similarities. Okay, maybe we start out with a very quick intro, just a quick recap of some of the Matlab things. So please, everybody, start Matlab. And everybody has downloaded that file? Yeah, good. So I may need to adjust the screen size so you can actually see what I'm typing. I think this may actually work. So when you start Matlab, you have on the right-hand side the folders, and I'm going to close this because I don't need to see the files, and this makes the other windows bigger. This is the editor file, or this is the editor. This is where we do most of the coding. So we type our codes in here. We can select this and, for example, hit F9 or go to evaluate selection. Then we will run this part of the code. That's similar to what we did in Python a couple of days ago. So usually it's a nicer thing to use the editor up here because you can make comments. You see every line that begins with a percentage sign is a comment, meaning these are comments that you make for yourself, where you say, okay, this is how I make a figure, or where you take your own notes, okay? And it's really important that you do that, because in a week from now, when you look at this code again, you will not know what you have done, right? So you need to take notes. That's your obligation. You have the option of generating what you call it, blocks or sections where you can separate the sections out by 2 percentage signs. So these 2 percentage signs means that up there, this is one block, and then a block follows below. So that means you can run those sections individually the same way as we have done the sections in Python, okay? That's usually a nice way of doing this. Okay, so the first thing we need to make sure that Topotools is installed. Does everybody has, or did everybody download Topotools? Okay, if you have not done this, I provide the link here. So this is a GitHub link that is in the top of the Matlab file. And if you copy and paste this into a web browser, you will have the Wolfgang's page, and you can clone or download this. You can download the zip, and you need to uncompress it and put it in your downloads folder or somewhere else that you can access it. And of course, you need, uncompress it, put it into a folder where you can access this, and you need to remember that that directory, because we need to tell Matlab where Topotools is located at. right? Because Matlab doesn't know it, where it's located at. And we want to find those commands. So we can use the command add path, and then we add this path. So here, for example, you may have to type, I don't know, whatever that file name is, C downloads, and then Topotoolbox 2 or whatever this is called. I don't know what it's called for you. We need to make sure that everybody has this, because otherwise we won't be able to follow along. So if you get stuck, maybe the experts can help to make sure that everybody has this downloaded, or the people who already have downloaded it, that you're able to add the tool, because add the path, I'm sorry. Otherwise, this will not work. Of course, you can copy the zip file onto a USB memory stick and exchange that too, okay? Yeah? So pretty much everything we do depends on this. So if you don't do this step, you will be lost the next 6 hours, okay? So it will be good that, you know, if you have a problem with that you let me know that this is the case, because otherwise all of the Topotoolbox commands cannot be found or cannot be used, okay? Okay, is this working out somewhat? Is someone completely lost? Is someone not able to open Matlab? And that I would say is completely lost. No. So for those of you who have installed it, you can check your installation if you type, for example, help slope area down in the command window. That's supposed to give you the help of slope area plots. If you see a help popping up, then you know that you have installed it. If nothing pops up, or if you get an error, a mistake, then you haven't properly set the path, okay? So again, really everything depends on that we do the step that you have Topotoolbox installed and the path added. Who is still lost? No, have you done this? You added this? Yeah, you have to run this, right? Okay, try it again, the help. You can just go up with a cursor. With a cursor. With a cursor. It was up. Go up. Yeah, here. Okay, you push it. Okay, you do it. I'm sorry. You do it the way you want it. Yeah. Okay. So that works. That's good. Okay, so is everybody able to pull up the help? Yeah? So these steps, by the way, you need to do every time you start this. And so, I mean, you don't have to download it every time. You just have to add that add path command, okay? And if you end up doing this every time, you may want to add this to the preferences to your standard directory path. Okay, so for those of you who know that they will be always working with topo tools, they can set the path to that directory where you have installed it. So if you go to the home ribbon up here and you have the option of setting the path and then permanently save this. This is essentially permanently saving that add path command that you just added. Yeah, for those of you who know if you were doing this more frequently. Good. Are you ready so far? Is that? Hmm?
When I'm giving this add path.
Yeah, run it. No, you have to, no, you don't want to run everything. This runs the whole file. This run button would run the whole file. You just want to run this line, right? So you do a right mouse click, and then you say evaluate selection, or F9 is a better option. Okay, this is not, no, you have to put it in quotes. It's a text, right? So make sure that every text in Matlab has to be put in quotes. So let's see if that works in. If you add this, okay. Find it. Okay, now type help slope area. Oh, no, hold on. You do Control V. No, you just deleted this command, right? Do Control V, you have to undo.
Control V is
Z for undo. Again, because you deleted that line, right? You type in here, you can either type, it doesn't matter. Have you worked with Matlab before?
Yeah,
okay. Help slope area. Return. Perfect. So it works. Good. Okay. So I assume that you have added the path to Topotools, and now you can access all of the commands of Topotoolbox. Okay, and now we can get going. So for those of you who are already familiar with Matlab and who want to go ahead, there is a PDF from Al Neely. And we describe some of those things in much more detail. So you can get that PDF from the GitHub page. We spent a long time writing this paper and describing many of the steps in detail. We also developed a GitHub repository for DEM analysis that you may want to look at. But everyone else, please follow along. So the first thing we need to do is we need to get the data in Matlab somehow. And what I suggest you do a change directory into the directory where you have stored your DEM. So maybe that is in downloads, maybe you have saved it on the desktop somewhere. You can either do this on the command line by typing cd, or you do it by changing the directory up in here. So here you have the option, and this line up in here, you see in what working directory you're located at, and you can change this by either going here or by directly clicking on the browse for folder, and then you can select the directory where you have stored your DEM. Please navigate there, okay? For those of you who prefer to use the command line, you can use the command cd, which stands for change directory, and you can navigate directly to that place. Okay? So the way I have set this up is that I am defining a variable. I'm defining a variable that is called the file name of the DEM. The file name, as we said before, is right, Poso USGS UTM11 blah 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 .tif, and that is my DEMF name. So this is my digital elevation model file name, and then I'm using the command grid object, which is a Topotoolbox command, and that Topotoolbox command allows to load a GeoTIFF file. So GeoTIFF is a very common way of storing data, right? And you want to get these data into Matlab, into a format that can be read by Matlab. And grid object does this thing for you. It not only loads the data, it also loads the projection information, the file format, and other additions. So this will all be stored in something that is called a grid object. Okay? And once you have that grid object, you can do all the analysis on this. So we load this. So I'm selecting those two lines, and I'm hitting evaluate selection, and then this is being loaded. This takes a second or so, okay? And now if you would type SCI DEM, you get to see that grid object. So that grid object, this is something that Wolfgang defined for Topotoolbox, and for that grid object, for example, has a matrix in it that is called Z, which is the DEM, right? Z is usually the height. And then it tells you more information about the reference matrix, the size of the array, and the georef information. And if you want to access those, you could, for example, type scidem.z, and then you would get a long list of the DEM, right? This is now plotting up on this. It's pretty meaningless, but there will be a way how you would access the array that you just loaded in, okay? Jesus. Okay. By the way, when you have an output that continues to go, Control C, CTRL -C is the way how you can break that. Okay? Good. Let me make this smaller again. So maybe as a first step, we want to see what does the DEM look like, right? It's always a nice thing to have some kind of a visualization of the DEM. The standard way of displaying images is using image, and then image is the word, and SC stands for scale. And so that command, image scale, will load the DEM and scale the color bar to the lowest and to the highest value, so that you automatically have the maximum contrast in there. So let's do this. If you do this, the image scale, you have a new window popping up with the actual DEM, okay? So that reminds you of what we have seen yesterday, right? That was the point cloud that we have looked at, yeah? Yeah, let me, guys, can you help here, please? So, this DEM is a little larger than the catchment itself, so we made it a little bigger yesterday so that it includes all the outer parts. Matlab has a nice way of also calculating a hill-shade image, and so there is a command, image scale HS stands for hill-shade, and that essentially calculates the hill-shade as we would do it in ArcMap or QGIS and puts it in the background. It's just a nicer way of displaying the data, okay? So here we are. So now you have a relief view of the DEM, okay? Everybody with me so far? Yeah? So those were the easy steps to look at things. Usually, it's always a good idea to look at the DEM before you start your analysis, because maybe there are NaN values. Maybe the no data value hasn't been set properly. Maybe something went wrong during the projection. It's always important that you look at it before we start the analysis. And obviously, you know, this looks pretty okay, right? So the first thing that we do, we talked about this a little bit before, and now DEM is perfect. You know, every DEM has some kind of a problem. There may be noise in the data. There may be wrong elevation points. So you need to make sure that your digital elevation model is draining, as you call it. Yes? Can you just type SCI? Oh no. You have not loaded it. No. Can you go up to the command? Have you loaded the file that? No. Up in here in the editor. Have you loaded the file from the GitHub? Yes. Yeah. Can I see the command?
I mean, I typed here only everything.
No. The file from GitHub, the first steps.
This one.
So this is. So please make sure that you follow exact. So Matlab is really stupid. Matlab only does what you tell Matlab to do, and if you Matlab doesn't know what you want you to do. So please make sure that you follow exactly those steps, and you need to make sure that. You define the file name first, and then you load the file name, okay? So what happened is, yes, and then you need to do the grid object command, right? No. This is different, right? It looks different on the screen, right? I did not say equals grid object, you know, it's only this grid object command. There is no parenthesis in there, right? Please get the GitHub code, yeah, the first steps, yeah? Because those are tiny little, you know, you just did one character difference, but that has a big implication for Matlab, yeah? So that's
So it is saying input must be a row vector of character. So when they are like running this one, these two commands, so it is like input.
Wait. Can I see first? Can you show me the DEM that this is there? Okay, this is there. Okay, then go into the
MATLAB.
and you can I see error must be file paths. Can you type DEM fname? Just what that variable gives you? Yeah. You know, you need to check if that variable, the DEM, the same thing, you know, you just want to see what the variable looks like. This is like debugging. Yeah? Okay, and where's your... And can you do an ls? Just type an ls, return that lists the that lists the directory. So here is your file, POSO-UGN CL2 DM1.tiff. And now try the grid object again.
Which one?
Yeah, the grid object command.
The DEM
The
file?
grid object command.
Grid object?
Yeah, the one, the grid. You type, no, it has to be capital, or you look in here. It's the grid object command, right? That. Or you have it in here too, right? You have it, yeah. And just hit return. Select this. Hit return. Now you did it manually, right? Now you selected it, and okay. Now it works. You need to type SCI underscore DEM, SCI underscore DEM equals grid object. No, just equals grid object. Okay? And now you do the same, and now you should have it. Okay? Yeah?
Actually, you have this one. So when I hit this one, then it error creates some error. Why? Like this.
Yes, so single quotes. We get single
Yeah. So here's a thing. So on Unix computers, you can use double quotes for delineating text. For the Windows computers, they only allow you to do single quotes. Okay. So for those of you who have problems loading it, change this double quote to a single quote. Okay. That will make things easier. So now that we squared away some problems, are we all able to see the digital elevation model? Yeah? That is not yet? Are you? Could you download them? Right, yeah. Okay, I think you're probably not in the right directory. Where did you save the file? Workshop, okay. Yeah. No, wait, I think we have to go in there, go CD, D workshop. It's easier to change the directory in there. Or you do it up here. You change the directory in here. If you hit on this button.
But he's in D workshop there.
Right, but
This one.
it's the easiest is to change the directory. Let's change the directory in there. See, and you can hit on this guy.
Where is it?
About,
Workshop
yeah.
lab. DEM.
Okay, and select folder. Okay, now you're in there, and now you can use that file name. What was it? Or can you just type in if you go in here, type ls for list, ls. Copy and paste this into the DMFF name. That's the name. In the F name, in the F name. DMF. Here, this guy. Yeah. And then you delete the grid object and you just say F name without parentheses. Yeah. Right. Okay, let's try this again. Then this is not correct. Can you go in there? Can you go and then go to that directory where it's supposed to be? Okay. I wanted to talk a little bit about what we need to do with the DEM before we can do the analysis, and you need to essentially remove all the artifacts from a DEM. And the way we do this usually is by saying we fill the DEM. So in other words, we hydrologically correct the digital elevation model, which means that we remove any things in the DEM. So if you're interested, I could explain it in more detail, but I think we just skip over this and we just say fill things. So the command fill things does this job for you. It essentially drains, it makes a DEM hydrologically correct. So what may happen in a DEM is that in a river system, you may have, for example, an error in a digital elevation model, so it blocks the river flow, and you want to make sure that it continuously flows. The next step would be generating. The next step would be generating a flow direction file. So this is essentially the same what we talked about 2 days ago when we talked about flow routing. So now we are applying a flow routing algorithm that allows us to flow route the flow along the DEM, and we always follow the steepest descent. So in other words, we had that discussion, right, where we had the where we were looking at a 3x3 neighborhood, right? And essentially, we are interested from this point perspective in what direction is the river flowing, right? So this is what we call flow direction. And Topotools generates its own flow direction structure. So we call that it's a flow object. It's an object that only contains the flow direction. And the reason why Wolfgang has done that is because they are really nice ways of storing a flow object as a network structure, and then it's much faster to access. So this is a flow object. So the flow object at a larger scale, if you have now many if you have many grid cells, just for the sake of simplicity, we say it starts out here. So this would be the main stem. Then you have other tributaries flowing in this direction, maybe a smaller tributary flowing in this direction, and then maybe something else is draining into this direction. Okay, so you have a flow structure where you say where is the steepest slope for each cell and in what direction is a water flowing for each cell, okay? So you have essentially a bunch of arrows that point to the next cell. That is a flow object. And from that flow object, we can perform the flow routing. We can say, follow along those lines. Now find me how those flows work out. And this is what we call a flow accumulation. So we are accumulating, we're adding up the flows. So essentially you can think about it, this is being the tiny little parts of a network, and the flow accumulation is building you the network to follow along the streams. So this is a command that would allow you to do this. This is a flow accumulation that is essentially accumulating this network. And Wolfgang has done a really good job in making this computative very efficient, so it goes very fast, even for a relatively large DEM that we are currently working with. So now the question is, what does this look like? Now we have essentially the drainage area calculated. So the drainage area can be visualized. So now we could, this is a map, we can look at the flow accumulation by opening up a map. And you see there is a line that occurs here somehow, right? So you can zoom in and you see there is actually a line. So one thing about drainage networks is that they are rapidly growing. So a drainage network has, it's accumulating the flow from upstream. If you think about a drainage network, right? This is our outlet. This is our drainage network. We have parts of the catchment that have only a few cells draining into them, like, only really the surrounding 6 or 9 cells. And then we have cells down here in the bigger stream that receive thousands or tens of thousands of cells because everything upstream. So you have ranges, you have values that range from very little to very big values. What you do when you have a large range of values over several magnitudes? You take the logarithm of it, right? So that's what you do. That's the same what you do in finances when you're dealing with money, right? So a better way of generating this figure is telling Matlab to take the logarithmic to the base of 10 with it, okay? And if we do that, we see that there is the river network emerging. We have to zoom in a little. And here we see the river network, okay? So we can also tell Matlab to add a color bar. So I'm just typing color bar and I'm bringing that figure back up. Here on the right-hand side, we have the color bar, right? And these are now logarithmic scales. What does it mean when I go from 2 to 3 in a logarithmic scale? What was that? Factor of 10. So factor of 10 difference, one magnitude, yeah. So meaning that the blue colors are 1, 2, 3, 4 orders of magnitude smaller than those yellow colors, okay? Meaning that the blue colors have 1 times 10 to the 4 fewer pixels than those pixels, okay? So that's scaling that we are currently looking at. So this is essentially the drainage area, okay? So this tells us at every single point we would know what is the catchment area upstream, yeah? So we now have generated the catchment area. And conveniently, we are working with a 1 meter DEM, which essentially means that every cell is 1 square meter, so we can directly convert this into square meters. If we would have a 30 meter DEM, we would need to multiply this 30 times 30 because every cell has 900 square meter units. Everybody with me so far? Yeah? You know, if you want to get fancy, you can also display your map with a hill shade. So you could say how do I do this? Let me see. We can use the same. Oops, that was the wrong one. Sorry, that was the wrong way. We can tell Matlab to generate a hill shade from the DEM and then plot the drainage area on top of it. So then it would look something like this. So now we have the background, the hill shade, and on top of it, we have plotted the channel. So we can see where the channel here is floating through and how it looks like. So the command for that is the hill shade command. You need to tell Matlab where is my topographic data stored. That comes first. And then you tell Matlab take the logarithmic of 10 of the flow accumulation and plot it. Okay? Yes? Hold on. Can I? Who has troubles calculating the flow accumulation? If you have a very old version of Matlab, like 2015 or 2016, they have used a different C compiler for some of the code. So the Matlab comes, or Topotoolbox comes with a pre-compiled binary, and those have been compiled with a newer compiler. And if you're using the old Matlab version, it doesn't run. But if I'm not mistaken, we can do the following. We can tell there should be an option. No. Let me just see. One second here, okay? I think you may get away with doesn't work out, where the pre-compiled version doesn't work out. Please delete the old maxw64 file. It's in the grid object, stream object, private directory. There you have a file that is called maxw64. In fact, it is, which file is it? Here in the private directory. Here, this, I think, You need to delete this. This is not you, only who had issues. I think there were only a few people, right?
I'm having this problem. Read object cannot read the TIFF file because it does not have a TFW file.
It has a not one?
It does not have a TFW file.
You don't need this. Just type grid object. And hit return. And then you select this. Maybe because you need the mapping toolbox. Maybe that's a problem that this is not included. I can. You have a memory stick or something. The other option is you copy it from someone someone else. Let me see. Matlab file then. So there should be an SCI Matlab file. You just copy it and say load SCI Matlab. And anybody else who has issues, there is a file that contains the DEM and the flow accumulation, and you can load this directly into Matlab if you have problems generating this file. Okay, so I make the assumption that you have now successfully generated the flow network, and this is what it would look like. And one thing you will notice when you zoom in here is that in the modeling domain, you model a stream. You know, this is a big stream. You actually can see the width of the channel, right? You see that the channel is several pixels wide, but that the flow accumulation only occupies a single cell, okay? So in that case, even though the channel may be several meters wide, it is only taking up one cell in the model world. This is really important, okay? So because, you know, from a modeling perspective, now all the flow is in a single cell going along a 1 meter cell, which is of course not true, but that's just the way how you implement it. Okay, so as the next steps, we want to threshold that flow accumulation somewhat. So in other words, we want to say, well, we are not interested in every single pixel. We just want to have the pixels that are really part of the stream or part of a river. And you know, when you think about a network or a hill slope, you know, if this is your hill slope, down here the rivers begin and then continue to flow. Usually you have some kind of a threshold area at the drainage divide where you don't have rivers flowing, where you have overland flow, for example, or where you have debris flows occurring, for example. So the idea is that we have to threshold this. In other words, we have to tell Matlab, don't take all the flow accumulation, only take the flow accumulation above a certain threshold. And we just set it to 1e to the 4 to 10,000 square meters. 10,000 square meters means 100 times 100 pixels. So in other words, up here, when we have more than 100 times 100 pixels, we just say the channel starts. There are separate algorithms that allow you to do a channel head detection to detect that channel head independently. We are not going there right now. We are just saying our channels start at 10,000 square meters. Yeah. So I'm saying the area threshold here is 10,000, 1e to the 4. Okay. This is something that you can, for example, verify through field work. If you have been in the field, you can take GPS points at the location where the channel starts. Some people have done that on the Seawallic anticlines and on other areas. So this is a very nice way how you could bring in your field information with GPS points, and then you could plot those GPS points, for example. You could plot them on this map. Hold on a second. You could plot them on the map. And then you would see, up here somewhere that the channel begins. So here, here I would argue that the channel begins somewhere here, where the channel starts to be turquoise or goes from green to turquoise, right? I think we could all agree this is a channel. This would be the hill slope, right? So más o menos at least. So turquoise just happens to be 1 times 10 to the 4. That's the 10,000 square meter. I think we can, I think we can convince ourselves that the channel head is somewhere around 1e to the 4. Okay? Because when we apply the stream power law only works for channels, not for hill slopes. On hill slopes, we have diffusion, right? Remember the linear diffusion modeling? We do that at some other point. Right now, we want to extract the channel network. There are really neat approaches to extract the channel network or to identify the channel head based on some geomorphometric approaches. Fiona Clubb has been doing that, but we are not going there. Right now, we just say we apply an area threshold. Okay, so when we apply an area threshold, what I'm doing here in the next couple of lines, I'm first getting the DEM resolution. That happens to be 1 because we're using a 1 meter DEM, so that's super easy here. But when you use an SOTM DEM, the DEM resolution would be 30, for example, or 90. So that's why I have this in here. Okay, and then I'm defining the minimum area in pixels, right? Because Topotools thinks in pixels. What is the numbers of pixels that I have upstream? But we think in drainage area in square meters, right? So we need to convert between square meter and the numbers of pixels, and that is just the minimum area pixels. So I'm converting that area threshold in square meters to the minimum numbers of pixels. Agreeable for this example where our drainage, where our cell size is 1, it's all the same, right? But I'm putting it here so that you know that when you use a 10 meter DEM, you would need to use this approach. And then what I'm doing is thresholding my flow accumulation with this minimum pixel approach. So I'm saying only pick out the pixels in my flow accumulation that are above that threshold. And I'm calling it flow accumulation underscore W for water, where I'm saying that this is the river. So if I am now, I can go up to my command, and I'm now plotting the new file, the thresholded file. And now we have removed many, many pixels, and we now really only have the channel, okay? So now the hillshade is completely empty. There is no channel on it because we just removed it. And now we have extracted, or now we are looking at the channel. And, we may now argue about it, well, this is part of the channel too. We could have changed, we could have used a different drainage area threshold. And you may be right, you may say, well, maybe a 1E3 or, 1,000 square meter would have been better. But I think we just say we use this, we want to be certain that we have a real channel, so we use 10,000 square meters. Again, this threshold will change from field area to field area, and that's where your knowledge comes in, right? That's where you need to, you look in the field, you see where the channels start, and you can use that as an indicator at what threshold you use here. As a ballpark number, this is a high resolution DEM, so that's why we can do those things. And when we use an SOTM DEM with a 30-meter spatial resolution or a 90-meter spatial resolution, the ballpark number is you use 1 square kilometer, 1 times 10 to the 6. Okay, so the rule of thumb for SOTM is 1e6 meters, which equals 1 squared kilometer. Okay, so this is the threshold area for channels for an SOTM DEM, because otherwise, you have a DEM with a 30-meter channel width, and the rivers need to have a certain width before you can even pick them up in the DEM, right? So that's a very different scale. So this scale, this DEM here, has a spatial resolution of 1 square meter. An SOTM DEM, let's say the 30-meter SOTM DEM, has a spatial resolution of 900 square meters per pixel, 30 times 30, right? 900 square meters. So this is almost 3 orders of magnitude difference in spatial resolution. Okay, so we are looking at a DEM where I think, this would be maybe 2 or 3 pixels, that entire area. So okay, so we are looking at very different spatial resolutions here. So we now can play those games where we say, where does a channel start? When you have an SOTM 30-meter DEM, you don't do that. You just say 1 square kilometer, and that's it, okay? Because you can't even see the channel. Okay. Now we can move on, and yes?
You can show again this command for them.
Yes, of course. Okay. This is the way, let me just pull out this figure. If you want to generate this figure, use this command, okay? So this is a command. And you can also move around in your figure. And I think we can all agree that that is, generally speaking, a fairly useful threshold that we have. Okay, so now we have a mask that that tells us where our rivers are. Okay, so this is a mask. It's zeros where there's no river, and it's 1 where there's river. It's a binary mask. You call it a binary mask. Now we can do the same. Now we can extract a new object, and the new object is what? No, hold on. Yeah, we can just delete this. This is just a repetition of what I did before. So what Matlab? So we just repeat those steps here, and then we are generating a new object that is called a stream object. So now we are extracting from the DEM a stream object that follows the stream. So we are throwing away all of the other hill slopes and everything else. We are just walking along the stream. So this is what we call now a stream object. And that's really important because this will allow us to calculate the slope along the stream and not taking into account the slopes that come in from the sides. So we are interested in the channel slope, and the channel slope is along the channel and not the stuff that comes in from the side, okay? So this is our stream object. And the nice thing about this, when we do this, is now we can actually say, plot this as this is now a file with X and Y coordinates, okay? And this gives us a stream network. So the same way as you would do a scatter plot, you are now plotting only the channel network because we have created a new object. a stream object that has the x and y coordinates. The x and y coordinates are in fact UTM-X and UTM-Y. Okay, so this is now our network that we have extracted from the digital elevation model. And with this network, we can do further analysis, right? Now we're in the channel world. Now we can say, find the slope along the channel, for example, yeah? Yes?
In case of SRTM, the DEM resolution, here what do we need to put, 3030 or what? Why it is 2?
No, this is automatically extracting. You can call this, if you call this, you can select this and call it and evaluate it. Okay. You will see it's 1. Okay. So you can call it and then you find out what is written in there. So, I don't know what the schedule is. Would we want to take a short break? Good, let's take a short break. Time for chai. And the first thing we do is that we have extracted that river network, and one thing you will always notice when you work with the digital elevation model is that you never exactly extract the catchment that you are interested in. So there will be lots of places outside the catchment. So you see those small streams that are located outside the catchment that are not part of our focus area right now. That's very typical. Whenever you clip out a digital elevation model, you always clip out areas that are from a different catchment. It's just the way it is, right? Because no catchment is exactly like a square. We can tell Matlab to just use the single largest stream. In other words, we can tell Topotoolbox that we want to ignore all those small channels and we want to focus on the smallest stream. On the largest stream. And the way we do this is we use the command K largest connected component. In other words, we are selecting the river network that has the most connected component. And this is the largest one. So this command accepts also the numbers of largest components. If we would put a 2 here, we would extract the 2 largest river networks in your DEM. If you put a 3 here, then you would extract the 3 largest river networks. For this example, we only have 1 river network, right? So we extract that river network and we essentially override the existing variable. So now if we now do the plot of the river network, our river network does not include the small things anymore around it. Now we only have 1 big river, okay? So that's one way how you can focus your analysis on the stream that you're most interested in. So next, I wanted to briefly show you how you can generate a somewhat nicer figure. So we now have created the digital elevation model and we have a river network. And wouldn't it be a nice thing if we could show it on a hillshade to have a nicer visualization of what we have done so far? You can do that with Topotoolbox. Here we are creating a new figure. Figure 1 just means we are creating figure number 1. We are using the hillshade of the digital elevation model, and we are also changing the ticks a little to make it look a little nicer. Okay, so the first 2 commands create our map in this fashion, right? We have the color bar here, and then we have the UTM coordinates that are put here, right? Then we add labels. Then we add an X and a Y label to tell us this is UTM easting and that is UTM northing. By the way, when you do river network analysis with Topotoolbox, you have to use a projected digital elevation model. It has to be projected, right? Because otherwise, the cell size would be changing of an unprojected file. So if you would use geographic coordinates, each cell would have a different size as you move away from the equator, right? Because there's a latitudinal dependence on the cell size. So you always must use either UTM or any other equal area projection. You may use a Lambert azimuthal projection. Usually UTM is a nice choice. Yeah. That just as a side note. So it's important to always use projected data. Once you have done the analysis, you can write it into a GeoTIFF file or a shapefile, and you can reproject that shapefile to any projection that you want. You can then reproject it back into geographic if you want. But the analysis itself needs to be done in a projected coordinate format, because otherwise, here we are assuming that each grid cell has the same size. If you use geographic coordinates, the size would differ of each grid cell size. So you couldn't do the drainage area calculation, okay? That's really important. Okay, so on this map, I want to add the river network, and I'm adding it by telling Matlab to hold onto the plot. So now I'm plotting a new file, or now I'm plotting the river network on top of this map. So I need to tell Matlab to hold on this plot. So now everything that I'm plotting on top of the same plot. And I'm plotting the river, the stream network that we just generated. Here it is. So here now you can see here in the black lines we have the stream network, and there is also the nice thing in the newer Matlab versions that when you move the cursor over the stream network, it's actually following the stream network, and you could extract exactly those coordinates from the stream network if you would be interested in this, for example. Anyway, this is a nice map that we can work with. That's something that you could save into a PNG or into a JPEG file if you would want to. Okay, there is another thing that you can do, which is maybe not that useful right now, but you can also delineate the drainage basin. So because we have a flow network, right? We have the flows of the river. We can identify the river, and when we can identify rivers, we can also identify the borders of rivers, which is the drainage basin. We don't need to go there because right now we only have one drainage basin there, right? This is this large catchment. If you have a different digital elevation model of several Himalayan catchments, for example, you may need to do something else. One thing you could do is, if you are interested in a very specific catchment, for example, in this guy here, if you, let me make this bigger so that you can see what I'm doing. So let's say I would like to extract a small catchment like this guy here, this catchment in here. I can click at the coordinate of the outlet. I just did this. So I have a UTM-X and a UTM-Y coordinate, and I can use that as an input in my drainage basin command to extract only the drainage network outlining that little catchment, if I would want to do that. So that's how you can select sub-catchments if you would like to.
Please repeat this.
You say what?
This sub-basin part. How we can select a particular sub-basin?
You need to get the coordinate of the outlet. So by clicking on near the outlet, you would essentially, you can also zoom in. So if I'm zooming in here, right, and I'm clicking on this guy here, I have the coordinates. Oops, I have the coordinates of that point, and I can feed that into my drainage basin. Drainage basins. So if you type help drainage basins, you have the option of adding the XY coordinates. So here in drainage basin, let me move all the way up. Here in the drainage basin, you give the river network, and then you give the XY coordinates. And then you would get that drainage basin that is outlining that catchment, yeah? So that way you could select a specific drainage basin because you have field observations from that drainage basin and you would like to include that, yeah? I don't want to do this now. We can do this later with the SATM DEM, okay? I'm sorry, what?
I'm not getting XY position from figure. I tried to click, but
I think that is a Matlab version. So my apologies to the older Matlab versions may not be able to do that. I'm sorry.
18 should
It should work.
Yeah, this one.
Yeah. Can you select on this guy? No, on the arrow, yeah? Weird.
Only these points are shown, but I don't know.
No. I'm sorry, I don't. Maybe it needs to be a newer one. One thing, what you could do. So if you have an older Matlab version, one thing to do is you can click on the data cursor. You can use the data cursor if
Yeah,
you,
data cursor.
and now it works. Good.
Yeah, it's showing, but it's showing in this format. So
That's okay. Yeah. Then you have to convert that. Yeah. I think it's a Matlab version thing. So. Okay. Let's do one more things. A few more things for visualization purposes, just because now that we have spent time on generating the network, we can do many nice things with the network. And one thing that I always like to do is to create a longitudinal river profile. So let me pull up my plot always. So one thing you can do is now that you have the river network generated, you can essentially extract the elevations underlying the river network. And that means that you're extracting the longitudinal river profile. So now you are in the river network world. You're following along the river network. Whenever they make curves, you make curves. And you can use the plot DZ command. So the plot DZ command plots along the river network. So now I am plotting all river networks in that file. So right now this is my river. All black lines are my river networks, and these are all the longitudinal river profiles of every single stream that we have in there. And now you may ask, is it useful to plot the river network or the river profiles of every single stream? I don't know, but maybe it's more useful to only plot the trunk stream, the single largest stream, right? So that's often what we then use as a longitudinal river profile. And you can do that by using the command trunk. The command trunk extracts the trunk stream, the longest path along a river network. And the way I have plotted this here is that I am plotting the trunk stream on top of the existing river network. So here I'm plotting the trunk stream in blue. This is the longest stream that exists, and I'm plotting it on top of the other streams, right? And now those of you who are familiar with river networks, you immediately see this is not a river network in equilibrium, right? What would a river network in equilibrium look like? It would be a nice exponential curve, right? And not with a big kink in here, right? This should not happen. I mean, of course it happens, but it just means that river is not following the theory, right? So there is tectonic activity, something going on that caused that kink, right? So you immediately see this in here. Everybody with me so far? Good. Because next step, I would like to talk a little bit about how we can use the DEM a little more to display other metrics, and then we dive into the stream power analysis. Okay, you all have heard about local relief, right? or the elevation distance between the minimum and the maximum elevation in a certain radius. That's essentially the relief. If you envision you're standing at a point and you draw a circle of 100 meters around you, and within those 100 meters you look at the lowest elevation and at the highest elevation. And that elevation you plot into that center pixel. That is what we call relief. So it essentially tells you how deeply has terrain been incised, for example. So Topotoolbox allows you to calculate local relief very, very fast. And it's called local topography. And I'm calling this on a digital elevation model. And I'm saying I'm doing a 200-meter radius, meaning I'm looking left and right 200 meters. And I'm getting the minimum and maximum elevation, okay? So this is our relief. And we, of course, that takes a second because this is a more elaborate calculation. Here we are. And now I am using, again, image scale hillshade. To plot the local relief over 200 meters distance in, oops. So here is the local relief. The color scale now is local relief, and essentially the higher colors indicate that, or the colors that are more yellow indicate that in those areas you have, for example, 160 meters relief, meaning that within a 200-meter circle, within a 200-meter radius, your elevation is changing by 160 meters. So that's a really nice way to see what parts of your landscape are highly incised. Yeah. So that's usually a useful map to show where you then see where you have the high relief locations. You know, for the Himalayas, you often do that to identify the regions that have been mostly incised, for example. So this is a map, or the data that you generated here is maybe something that you would like to bring back into ArcGIS or into QGIS or whatever your favorite GIS system is. Topotoolbox allows you to write any matrix or any array back into a geotiff file. And the command for that is grid object to geotiff. You know, this is a grid object. The relief that we calculated is a grid object. And we are writing it into a geotiff file, and we just give it the name, okay? And that file you could open up in QGIS or ArcGIS. And you can also reproject it to whatever projection you would like to have it in. Yeah, so this is a really useful way how you can export some of the information that you have generated. Okay, next I would like to talk a little bit about stream power loss and how we can use that river network to extract something more useful, potentially steepness indices. And I'm just asking the question, who is familiar with log area, log slope plot? Is that something that you have heard before? Yeah, good, at least maybe a few. Let's see. Okay, maybe we start with it very slowly. The idea is that you would like to characterize what a river is made out. And there is a stream power theory, and I prepared a couple of things that I would like to talk to you to. So let me, should I use this? Or I prefer to use this guy here just because it's a little higher. And I have to really bend down when I'm writing on this board, okay? So that's, okay, so we heard the term stream power model a couple of times before. I just want to recap some of the things that we have been doing. I'm certain Jérôme Lavey has talked about this too, because he's an expert in that field too. So the stream power model, you can formulate the stream power model in the following way. We say the elevation change through time, dz dt, okay? So how does a point along the profile, along those profiles that we just plotted, where did it go again? Did I remove it? Yes, of course I removed it. Dz dt is equals some uplift rate, something that is pushing up the river profile, right? Minus the erosion that is occurring. And the erosive term is essentially a constant. And then the theory or the empirical approach says that erosion is somehow proportional to some area term. That's the drainage area in that sense. And to some slope term. So instead of slope, I'm now writing dz dx, right? Okay, so we have a term that is telling us the change of elevation through time. This is not in space, okay? That's the change in elevation through time is equals uplift. That's the upward vector. And this is the erosive vector. And the erosion is usually a small constant k. And then it means the drainage area means the larger the drainage area, the more discharge you have, the more erosive power you have. This is what this A term tells you. And then you have a slope term. The slope term essentially tells you the steeper the river, the higher the erosion. Makes sense so far, right? And both of it is scaled, the area is scaled by the exponent, by the power law exponent m, and the slope is scaled by the power law exponent n. So now, because modelers are a lazy bunch of folks, they usually assume a steady state condition. And for a steady state condition, you set dz dt 0. This is 0, right? You say that uplift and erosion is balancing each other, right? So that's a basic assumption. And if you set this to 0, you can essentially, then the equation looks like 0 is equals u minus k times a to the power of n dz dx to the power of n. Okay, and now you can rearrange this, right? You can move this term on one. So we are interested in this term. So we want to bring this onto one side. So we rearrange this that we have u divided by k times a to the power of m equals dz dx to the power of n, right? I'm putting this on the other side and dividing by k times am. And then I need to remove this guy, right? So the nth square root or to the power of 1 over n is the way how you would do that, right? So I'm rearranging this to dz dx u over the k to the power of 1 over n, which is the nth square root of this, times a to minus n over m. Yeah? So now we have a slope term, some kind of an uplift divided by a constant term, and the area term. And that usually is being rewritten as S, because this is slope. dz over dx is our slope now, right? And we call that ks. We call that a constant. We call that ks. And we have area. And I don't want to write n over m. I'm just saying theta is equals m over n. And then I'm saying a to the power of minus theta, right? Then I can revert this and so on. So I end up having S, the slope is equals some constant times the area to some power. Okay? Well, we can use this too. So what we now we have an approach that allows us to measure slope, right? We can measure slope along the river network. This is our river network. We can measure the slope along the river network, and we can also measure the drainage area because that's the flow accumulation, right? Let me just make sure that my screensaver doesn't turn on, okay? So those are two things that we can actually derive from the digital elevation model. That's why we went just through that pain doing this kind of stuff, you know, because we can actually derive those information. And in fact, you could rewrite this to say our Ks is equals S divided by a to the power of minus theta. Okay, we are just rearranging this. So which means if we have slope and if we have area, we can determine for example, the steepness, that's Ks, or we can determine the concavity. Our M over N is the concavity index. That essentially tells us how convex or concave, no, not convex, how much concave is our channel, you know? Does our profile look like this, or does our profile look like this, you know? So this is the concavity. And the steepness tells us, do we have a channel that is really, really steep or a shallower channel? So let me just draw this in the way how we mostly use this relation, and I want to keep this. No, I don't need this, or do I? I don't know. So if I now have a plot, if I now would plot drainage area against slope, essentially my relation that I just had, that I just erased by the way, my relation tells us if we have a small drainage area and here a large drainage area, for example 1E7, and the slope is usually given in meters per meters, and the drainage area is, for example, square meters. It means that with increasing, the exponent is minus, with increasing drainage area, we are decreasing the slope, okay? And because we have several orders of magnitude of slope and several orders of magnitude of drainage area, remember the log 10 we did earlier for the drainage area, you usually say log area, log slope, okay? So log area, log slope means that if we are standing at the top of our channel, at the top of the drainage divide, and we are starting to walk down our channel, and at the very top, the slopes are really steep, right? You know the degree flows that happen up there. You have really steep slope at the top, and when you start walking downstream, the slope decreases, right? So you end up getting some kind of a relation that looks like this. And because this is what we call a power law, right? We have a log area and we have two log axes. A power law means it's a linear feature in log space, right? So we can draw a regression through this guy here, and that regression tells us the concavity. This is our theta. So the slope of this line is, how steep is our river? How curved is our river? So that essentially means, that tells us how do we change curvature of the river along the drainage area. If we're going down And if we are going down a lot, we would, if we have a higher curvature, we would have points that would, for example, look like this. And then we have a higher theta. So this line gives us the curvature, okay? That gives us how curved is the terrain, because essentially this is an x distance, right? That's distance downstream, and that is the slope of how fast is the slope changing. So we're going downstream and we're looking at how the slope is changing. And if the slope is changing fast, we have a steep relation, which means that we have a high curvature, okay? So that's the relation back to our, now we have distance versus elevation. This is this guy, right? So this guy, this is a higher curvature, this is a lower curvature. This is expressed in the steepness of this line, okay? That's our theta. So this would be a small theta, that is a larger theta. The steepness index is essentially the y-intercept of this line. This line is intercepting at some point with the y-axis, and that is our Ks value, right? So in other words, the higher the intersection with the y-axis, the higher our river steepness, okay? So we can envision this in the following way. If we have, again, log slope, log area. So if you change the river in this direction, you are changing the steepness. So essentially the intercept is changing. So the higher the river on the log area, log slope plot, the higher the slope per drainage area. So think about it. For a given drainage area, you go up the drainage area and you see a certain slope. And if that slope is higher, then it means your river is steeper, right? So if you have a steeper river, you're moving your log area, log slope relation up this way. If you have a river that is more curved or more concave, you are changing your relation. You don't have that. That's essentially a straight line. You don't have that concavity. So you're changing the concavity. You're changing the slope of that line. Okay, there are two parameters, right? When you do a regression, there are two parameters. One parameter is the slope of the line. The other parameter is the y-intercept, like linear regression, right? So the slope is the slope of that line is a concavity, and the y parameter is a Ks. Okay? So what does that mean for the steepness index? In other words, what we are interested in, or what many people plot, is the Ks, is that y-intercept of that regression. We are going to do that in a second, okay? Because the y-intercept, of course, depends on the initial slope, right, on the concavity, and you want to be able to compare different steepness indices with each other. You set that theta to 0.45. That is a global study that argues that globally the concavity of the rivers is roughly 0.5, and you set it to 0.45. So you fix the concavity at 0.45, and then you're just solving for the y-intercept. You're just solving for where does it cross the y-axis, and that gives you the steepness index. So the reason why you do that is because you want to compare channels from one part of the world to the other part of the world, and if you have different concavities, of course you will have different steepnesses, right? So you need to fix the concavity, and the general agreement is that you fix it to 0.45. Okay? So that makes it actually a very easy regression, because you fix that parameter, you only have one free parameter, and then you fit that through 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 all the measurements that you have. It's fairly straightforward in that sense. Are there immediate questions to this? Should I repeat something? I know that was really short. I usually spend 2 or 3 hours explaining this, but I was assuming that you have heard some of those things before.
The 0.45 is for Himalayan-like terrain or for
Global. You know, I always think the Himalaya is the world, but no, this actually means is global. Okay, so it actually means this is done from a global perspective. And the other important thing is, I don't know if you're familiar with power laws. The other important thing is, you need several. This only is true for several orders of magnitude, meaning that when you're looking at catchments from 1 to 10 square kilometers, this is not going to work. Usually, you want to have, ideally, 3 orders of magnitude on the x-axis. Okay, so let's say your axis here goes from 10 to the 4 square meters to 10 to the 7 square meters. Then you should be good to go. Or 10 to the 6 to 10 to the 9 or something, right? But fitting a power law through only 1 order of magnitude is not a good idea. Okay, so that I see many people do that. Just don't do it, because it's, from a mathematical point of view, you know, that's the logarithmic axis. You're trying to fit, if you only have 1 order of magnitude, you wouldn't need to take the log of something, right? It's not meaningful. So you need to have several orders of magnitude here. Yeah, the same with the slope axis. The second comment that I want to make, that is what you call bedrock erosion. So if you have a long fluvial stream, such as the Amazon, for example, this will not work on the Amazon, because then you have sediment transport processes and not incision occurring. This only works for mountain terrain. So this works really well in the Himalayas or the Andes. But if you want to do the entire Amazon from the Andes to the outlet in the Atlantic, it's not going to work, because the river profile would be steep in the Andes, and then you have a really long slope river profile through the Amazon basin, right? So your log area, log slope plot, the slope here then doesn't change. The slope doesn't change over several orders of magnitude while it stays here. So of course you couldn't fit a power law to it. The same with the Ganges plain. You don't want to, when you look at the Ganges River, for example, you stop when it leaves the mountain front. You don't want to have it continue the entire time when it flows in front of the mountain range, because you have no bedrock there anyway, right? It is a sediment-driven river.
this unit is meter square, no? 1 from 1 to
Area, the area is meter square.
No, sir, this threshold.
You mean this one here?
Yeah.
Yeah. I mean, so always a good rule of thumb is, you know, numbers you should remember is 10 to the 6 square meters is 1 square kilometer, right? So this is something that you should know. And then you can go left or right, go up or down from that. So then things is easy to remember. Okay, with this, so does that make sense so far? Let's look at some real data, and let's see how, you know, this sounds logical until you really see the mess of a log area log slope plot, because it looks really messy when you do this kind of stuff, right? And you need to do a lot of smoothing. Okay, so the idea now is that we say we need area and we need slope, and we have both for the river network, okay? So what you do is, moving in here. I'm sorry, what?
We missed the syntax for relief, for image showing for relief.
The local topography. The syntax is local topography, the DEM, and then the radius over which you would like to calculate the relief.
For the figure, that after
I'm sorry, what, up or down?
In line number
Line number what?
64.
Okay, here I just plotted it in, and color bar just adds the color bar on the side. So one thing I should say before we can extract slope and area, we need to make sure that our DEM is well conditioned. And because we did some filling of our DEM and because there may be artifacts in the DEM, you usually impose a minimum gradient. So you say you want to make sure that your DEM has at least that gradient. So here I'm talking about a gradient of 0.0001 meters per meter. So I'm talking about a millimeter change in a meter distance. I'm imposing that so that there are no flat areas, because flat areas by definition don't exist in a digital elevation model world. So I'm setting a minimum gradient, and I'm saying all the pixels that have a lower gradient than this, they should be set to 0.001. It's just a way to deal with artifacts. It doesn't have any physical meaning in that sense. It's just a way to deal with the artifacts. So I'm doing this, and then I'm actually calculating the slope. And now the nice thing of Topotoolbox is I tell Topotoolbox to calculate the gradient, and I'm not referring now to a 3x3 window moving gradient, like we did the other day, right? Now I'm calculating the gradient along the river. So I'm going along the river, and I'm not using a simple 3x3 moving window. That's really important because the slopes along the river are lower than what is coming in from the sides, right? So your slopes otherwise will be dominated by the hill slope angle, and we don't want that. We want the actual river slope, the slope along the river. So I'm telling Topotoolbox to take my river network and take that minimum gradient DEM that I just did here, so that I have a DEM where we at least have a tiny little gradient in it, and I want the units of tangents. The units of tangents means meter over meter, right? So it's dimensionless. I don't want to deal with degrees. You usually use meter over meter, because then your x and your y-axis have the same units, or at least they are in the same space, okay? So now I have a file that contains the slopes, and what else do I need? I need drainage area, right? So in drainage area, I can get by using the flow accumulation, and the flow accumulation I just multiply times cell size. In that sense, it's times 1 because we have a 1 meter DEM, but if you would have a 30 meter DEM, then this variable here would point to 30 meters, and then you have to square it, right, because the length is 30 times 30, so you have 900 square meters. So this is your area. So now we have generated the 2 data sets that are necessary to plot log slope versus log area, okay? And then I'm doing this here by using the Matlab function log. So log is using a log y-axis and a log x-axis, right? So I'm plotting this, and I'm adding the labels, and I'm adding a grid to it, okay? So let's look at this guy here. So now this is the log area, log slope plot. And that looks pretty ugly, huh? That certainly has some scatter in there, but that's just the way it is. But nevertheless, I think we could all, somehow we could all agree to the fact that this guy is going down here somehow, right? So there is somehow we can interpret that there is a linear feature in here, right? And now the question is, how can we make this look a little nicer? Well, this is a log-log relation. It's a power law. There are many very good publications of how you deal with power laws. Aaron Closet is one of the persons who has developed codes how to deal with power laws. And the way how you would do a regression through this function is by applying log binning, logarithmic binning. So you don't fit a regression in log-log space through all the data points, because that would mean that this end of the data would dominate everything, right? Because you have orders of magnitude more small pixels than you have large pixels. And you want the pixels to be equally weighted, right? If you would do a regression through this, you know, it probably would look like a line or something, because you only would, the whole regression would be dominated by this fact, right? So you need to do log-log binning. And usually you say you generate 100 log bins. Log bins means that the log binning is small here, and then it becomes bigger and bigger while you go along the x-axis. And you log bin the x-axis and the y-axis. So, and then you end up with 100 bins. So I'm not going into detail how you do that. I'm just letting you know that it's not meaningful to fit a linear regression through the full data cloud. You need to do a log binning approach. Okay, and the way you can do that, or the way you can Matlab or let Topotoolbox do that for you, is by using the function slope area. So the slope area function does exactly that for you, the log binning and the fitting of the regression, okay? So the slope area function takes our river network, it takes the DEM, and it takes the flow accumulation. And it does what we have done manually before up here, where we calculate, where we extract the slope and the river area. And then the slope area function does, on the area, it does a logarithmic binning, and it takes the median of every bin. It does the same along the y-axis. So in the y-axis, it also does along the gradient. It does a median binning, and then it fits a regression, and it allows the regression to weigh each point it allows to add weights so that you have a weighted linear regression in log space, which is usually called a robust regression, okay? So when you do that, you end up getting a bunch of variables that are then stored in the slope area plot, and here are then stored. Now you have 85 bins for your area. You have 85 bins for your slope. We will plot this in a second, okay? And you have the KS. The KS is the result of the regression, the y-intercept, okay? And this is our setter. It also fitted the setter, which is the concavity, which is close to the 4.5. It's not exactly the 4.5, but pretty okay, right? Okay, let's plot this. I think that will help to visualize this. So I prepared the figure here where I'm now plotting. I'm doing this one by one. I'm now plotting all the data points. You can see them in here. I plot them in light gray, okay? You see all the data points in here. I call that you know, it's a point cloud. And on top of this point cloud, I am now plotting the results of the regression. So now I'm plotting the log binning. Here are the log bins. So now when we do the regression, we only fit the regression through those 85 bins. We are not fitting it through the 100,000 points. We are just fitting it through those log bins, okay? And when we do this, when we do the regression, keep in mind we use a weighted regression, so we throw out the ones that are a little more noisy, the bins. This is what I'm doing here in the next plot. And I'm plotting the regression line. So this is now the line with a steepness of minus 0.41. Right, that's what we just had, and a Ks value of 11 or something that we had. That's the steepness value. Okay, so this is the steepness analysis that takes that channel, performs the regression, and assigns a steepness value and assigns a concavity value. If we now want to take it a step further and want to force the steepness index. So in other words, we just calculated what we call let me just see. We just calculated what we call the Ks and the theta. If you want to have KSN, theta is fixed to minus 0.45, right? Because then we have the normalized steepness index. The N stands for the normalization, okay? So if we do the same regression, and right now we allowed both the slope to change and the y-intercept to change. We can do the same regression by fixing the slope to 0.45 and rerunning to recalculate the Ks. And that's then what we would call the normalized steepness index, the KSN. That's what everybody talks about, right? That's the normalized steepness index. So, and I'm doing this here. Let me just, this is the next line. I'm just pulling this apart here. And all I'm doing here in the next line is I'm setting the theta to 0.45. So I'm telling the slope area command, when you do the regression, force the slope to be 0.45. And then do the same regression again. So let's do this. So if I'm selecting all of this again, and then we maybe can plot it. I mean, it obviously will be very similar because the difference between 0.41 and 0.45 is not that big, but you have other channels too, right? I mean, sometimes the difference is bigger. Anyway, I should have added a title. You could add a title and then say steepness index with theta equals 0.45. That's then the KSN, and that would just be the steepness index without the normalization, right? Because we allowed the theta to vary a little. Okay. My suggestion is you spend a few minutes with those few lines to familiarize yourself with what we have been doing. So the lines that start with figures, where I have the figure section, where we first do the log plot of the raw data. By the way, if you would change this to a different color, the gray gets a little darker if you don't want to have the dots to be that high. I usually like to plot the dots in the background of the raw data just to show you how variable the raw data is. If you would only plot the log bins, if you would only plot the black squares, it would give you the impression there is not that much scatter in the data, right? So that's, it's like fake news. You're massaging your data in a way. So I just like to have I just like to have this in the background so that you are, like this. Now you can see the data better, that you see that there's actually lots of scatter, right? So that KSN fitting is a pretty nasty business, right? You're really fitting to lots of noise in there. Yeah? So maybe try to reproduce some of those things and then we discuss them. So for example, you could generate plots with theta varying from 0.4, 0.5, 0.6, meaning that you have different concavities, okay? So let's do that. So the task would be make plots, plot theta equals 0.4, theta equals 0.5, and theta equals 0.6. Add title, yeah? You add a title to those plots, that you have three plots with a fixed theta using these area and slope data, okay? And then we will compare those plots to get a better understanding what the theta means for our regression. I'm doing the same here. I'm just taking out this part and So are there questions? Can I help? Does this make sense for you so far, or is this way too spacey? Very good, very good. I just wanted to briefly talk about what we can do. So this is. I'm now pulling up the figures that I just generated, right? These are the steepness indices. The one here with theta equals 0.4, 0.5, 0.6, and you can see that this line is changing, right? The 0.6 is the steepest. Steepest is meaning that for the same drainage area, you have the lowest slope at the outlet. Okay, so at the maximum drainage area, that catchment has a drainage area of what is it? 6 square kilometers, I think. You have then the lowest slope, the higher your concavity, because you are carving more, right? Your river is more concave, so therefore a higher steepness index just means that you're attaining lower elevations faster. So that's something to keep in mind. So these are the differences of the different concavity indices. The truth probably lies somewhere in between. Okay? Yes?
These whole three images, see that the y-intercept is same for this also?
No, the y-intercepts will be different. Very true. Very true. And that's why it's so important that you that you spend some time finding the right concavity. Because of course your y-intercept depends on the slope of the line that you're fitting. So your Ks will be different.
You can fix the y-intercept and change the slope.
Well, no one has done that so far, but theoretically speaking, yes, you could. But then you would need to know what the y-intercept is, right? And then you would need to know the steepness. So usually what people try to do is there are other approaches to estimate the concavity from a longitudinal river profile or something, and so that's how you fix a concavity. So usually you say your concavity is fixed to 0.45 or something along those lines, and then you have that fixed and you just look at the y-intercept at your KSM. One more word about the concavity. Usually, when you have very different lithologies, when you have soft lithologies, such as shallow marine shales that we have in this catchment, and when you have granitic rocks somewhere else, then you expect the shape of the rivers to be different, right? You expect a different concavity. And in that instance, it doesn't make sense to use one concavity over the entire landscape anymore because your concavity will be changing. Then you need to break apart your landscape. Then you need to have the catchment with one lithology, the catchment with another lithology, and process them differently because they will have different concavities, which means that all of your steepness indices are messed up too. So you need to make sure that you apply the right concavity. So usually, when I see a plot like this, where I can see that I fit a line through roughly somewhat, I feel comfortable using one concavity. If I would do the same plot over a much larger drainage area for a Himalayan catchment, where I'm mixing higher Himalayan crystalline, maybe with seawall lakes, maybe with lesser Himalayan crystalline, so very different strengths of rocks. I know that I have different concavities. Then your scatter along the y-axis is even larger, right? Because then you have low slopes and high slopes for the same given drainage area, which then reflects different concavities. Then you need to separate out your data and process those catchments separately. So then there are other automated approaches that you can use in Matlab Topotoolbox, where you say, for example, find me all catchments that are 10 square kilometer and fit that to all of those catchments. So don't use the big catchments anymore, fit it to the small catchments, and let's look at concavity afterwards.
Okay, for different lithology.
You say what?
For different lithology, the theta value is fixed, or we have to hit and try?
Well, it's not only lithology, it's also rock fracturing. If you have the same lithology that is fractured by faults, it will be easier to erode, and you can get much more concave profiles. Where when you have the same lithology that is not fractured, you can have, you have a very resistant rock, then you have less concave areas. So it's hard to say what the right concavity value is, but usually you spend a while looking at the variations of your concavity index. If your concavity index only varies between 0.42 and 0.47, that's fine. But sometimes the concavity index, for example, for glacially affected areas, they happen to be much higher, right? Because you really carve in a much more concave channel. So that's why you have to remove glaciated areas from your DEM before you do this analysis, because otherwise your analysis would be biased. So, concavity is a tricky issue. You need to spend time looking at the data and seeing if you can convince yourself that one concavity is fine. Most of the time it's not, but most of the time people still use one concavity. And because of that concavity issue, many just say, oh, I do KSN. I set my concavity to 0.45 and leave it there. Even so, it may not be the best concavity. Yeah? But, I guess my answer is you need to spend time looking at the data to convince yourself what concavity to use.
Basically, that regression line should match with that black dots.
And essentially your scatter should not be too large. So remember, did I remember that geologic map that I was briefly showing earlier? Let me pull it out again. 1 second, okay? I have this paper from Fiona. From Fiona Club, it's on the GitHub. I just want to show you one thing in here, and that is the geological map. Okay, so this is a catchment. We have low, very soft rocks, very hard rocks, in very simple words. Okay, so volcanoclastic and shallow marine sediments. The reason why we have so much scatter in this plot here is that why we have so much scatter in this plot is that we are mixing different lithologies. We are mixing the soft and the hard lithology. And if we would plot only the hard rock lithology, we probably would have a much lower scatter versus the soft rock lithology. So essentially, the rivers here are much steeper than they are here. So that leads to more, where did my figure go? This then leads to much more scatter on the y-axis, okay? So that's the point where now we are plotting a log area, log slope plot for different lithologies. Maybe not that useful, yeah? So that's where you would need to dive in and say, I need to break it apart, yeah? But nevertheless, this is the average steepness index for that channel, for that entire catchment, ignoring the different lithology aspects of it, right? You just need to understand how this is being produced, and it is being produced by mixing hard rocks with soft rocks, which of course will lead to more scatter. If you would do the regression separately, then maybe you would have two different concavities. In fact, you do have two different concavities in that area. Yeah? And this is a 6 square kilometer catchment, a tiny catchment. And things are already complex. Now think about a 10,000 square kilometer catchment in the Himalayas, and things get, way too complex. So that's why we, average over some of the things. Let's move on and let's do one thing that I like doing, and that is turn this into a map. So we now have calculated that regression for that entire catchment, but at the same time, let me just close my gazillion figures that I have here. At the same time, we could use the actual gradient value for each pixel and the actual drainage area value for each pixel which we have, and apply our equation. So in other words, we can say we are not doing a regression, we are now staying in map space, and in map space for each pixel that is part of our river, I'm just saying this is our river, okay? We have, for each pixel, we have the gradient and we have the area, right? Because we have that from the DEM. So now we can say, for each pixel, we just apply our equation, gradient divided by area to the power of theta, right? So this is this equation here, right? So we can now say, we want to calculate our steepness index for every pixel by taking the slope at every pixel, the drainage area at every pixel. We scale the drainage area with our theta exponent, and we can generate a spatial map with a Ks value for each pixel. And if we want to generate a Ksn value, then our slope area theta should be, if our theta is fixed to 0.45, we have a Ksn, right? So that's a simple calculation that, does this for every pixel. So if I'm doing this here, Horizon then. And then I have a new array, and that array is called SCA, Santa Cruz Island KSM. And if I plot this map, I now have the KSN value along the stream. So you see the color changes. The color changes are essentially the KSN values for each of the pixels, okay? So instead of doing the regression through all of those points that we just did, now we do the regression for each of the pixels individually. Yeah, so this is a nice way of creating a map that visualizes the steepness index. And if you look closely at it, you see that that's what you were asking with the lithology. If you look closely at it, you know, at least I have the impression that up in here where we have the more resistant lithology, we have more reddish values, right? So this is their stuff is steeper. And then where we have the soft lithology, it generally looks a little lower. And then we have the main stem and or the trunk stream, and that's where we have, you know, those turquoise value 20 to 25 KSM. So one thing that I note when I look at this map, it looks pretty speckly, right? It looks pretty noisy in that sense that, you know, every little bump in the river can cause a red or a blue value in here. So maybe we kind of want to smooth this map a little. We want to smooth along the river. For example, we want to aggregate values along the river. There are different ways of smoothing this map. We can use a simple aggregation command that the aggregate just essentially summarizes pixels into a larger length. So for example, here I'm defining a segment length of 100 meters, and I'm essentially taking 100 meters means 100 pixels, right? We have a 1 meter spatial resolution, and I'm just saying make this smoother by 100 meter, right? So now I'm having a somewhat nicer map that clearly shows that the more resistance rock have much, much higher steepness indices, and the softer rocks, okay, off and on you of course have steep areas. Other areas are much shallower. And essentially every single red area in that sense is a nick point, right? Every red area means you have an abnormally steep area, abnormally steep compared to the slope value that you would expect at that drainage area. Okay, so now we can look at this for a while. We could also, what we could also do, hold on here for a second. Oops. What did I do? We could plot image scale hillshade, SCI, DEM, SCI, DEM, color map, gray. Let me see if that works. There we go. So I'm just plotting the DEM in the background so that we have a better understanding of where we are, and I'm making the line width a little bigger. But this is one way of visualizing this, where we have a hillshade, a gray hillshade in the background, and here we see the steepness index on top of it, okay? So that's a map of the steepness indices. So the way I've done this here is that I'm using the first, I have my steepness indices calculated, I'm aggregating them, and then I'm generating a hillshade map. I hold on to the plot, and I'm creating a color plot of the aggregated files with a slightly larger line width, and I'm scaling my steepness index from 0 to now 70. So I changed the scaling a little so that you see that only the orange reddish part are the really steep sections. So most of the steep sections are here in the volcanoclastic, in the more resistant rocks. Actually, I think maybe 60 is a better value. Yeah. So the last thing that I wanted to do, because this time I think we stop at 12:30 when lunch is, right? Yesterday it was a little too long, I think. My apologies. I just wanted to let you know that we can also use a different smoothing function. So if you don't want to aggregate, but you want to rather smooth, there is a difference. I'm not going into the details of the smoothing function, but there is a way of smoothing that generates a slightly smoother output. Yeah, it's a figure here. So either way would work fine. Either the aggregation or the smoothing. The advantage of the smoothing is that you are keeping the steep high values. So in other words, when you aggregate, it means that when you have a bunch of, I'm using this thing here, aggregation means that when you have a bunch of values that are, if this is, now I'm drawing the river profile, if this is the river profile, this is a section of a length of 100 meters, and on top of this river profile, drawing the steepness indices. So if these are your steepness indices, low, and these are low steepness indices, so this is your KS, then aggregation means that you are essentially taking an average here. You would use that as a steepness index over 100 meter lengths, whereas the smoothing function maintains those peaks so that when you smooth it, it would rather look like this, okay? So then you maintain the peaks in a better fashion. So that's just the difference between aggregation and smoothing, so that you then end up representing the higher steepness indices in a better way. Well, so I suggest using the smooth function if you're going to aggregate or smooth your plot. And the last thing that I'm saying here is that you can export this file that we just generated. This is a vector file, right? It's a vector data set. We can export that as a shapefile. And that's something you can load in ArcMap, QGIS, or GMT, whatever you're using. So this allows you to do the more sophisticated analysis in Matlab and then write it to a shapefile and make your final map with ArcMap or whatever you're using. And so you do that by generating a map structure, stream object to map structure. And here you can give a segmentation lengths again. So now I'm generating 50-meter channel lengths because I don't want to write a vector file with a data point every meter because that would be way too much. I want to write a vector file with this, for example. And here I'm saying take the mean every 50 meters of my smooth value and not only store KSN, also store the drainage area and store the channel gradient, so that you could make maps of channel gradient, of drainage area, and of KSN. and you write this with shapewrite. Shapewrite is then the function that writes it to a shapefile, and you can open that shapefile in QGIS or any other software.
So can we get these values in Excel as an Excel file?
Excel.
Yes. If I want these numerical values.
Sure. You could save it as a text file. I mean, you know, this is, if you look at this here, the SCI smooth value is just a long list of text files. And you have the coordinates in the river file. You can, of course, you can generate a text file. And with a text file, you can then do whatever you want to. So for example, let me just see. So your structure, your river network structure, yeah, your river network, the stream object, has X and Y coordinates. And you can save your X coordinates and your Y coordinates and whatever else you want to a text file. And then you can load that in Excel or anywhere you want. Yeah? So. But you know, when you bring it into Excel, you lose the spatial information, right? So, I mean, unless you have the X, Y coordinates. I mean, all the analysis you would do in Excel, you would do in Matlab. And making maps is a nice thing in ArcMap or QGIS, for example. So I suggest that you try to do all the analysis in Matlab. The maps that Matlab produce are not that nice. So you can produce better maps with QGIS or with ArcMap, but you can't do those fancy analysis. You can't do all this fitting and the smoothing. You can't do that in ArcMap, at least not to the same degree. So it's nicer to do that in Matlab, and then you write it as a shapefile or you write it as a text file, anything you like. So before we take a break here, are there questions? Should I repeat something? Is there anything that is not fully clear? I think the most efficient way of practicing is that running through some of those things yourself in the code. That's why I'm providing the code for it. Maybe you look at this a little, and then after lunch we talk about it again, maybe discuss some points, and then I would suggest that we, we could either go in the chi-plot direction, that we do chi-plots, or we pull out a DEM from the Himalaya and we do this at a 30-meter spatial resolution. You know, it will be a very different scale, very different scale. We won't be able to see the individual channels. We are looking at, you know, mountain valleys in that sense. Or we can do both, either way. Okay, then let's take a break, and then we come back and talk about chi-plots. Let me get back. It should be mostly the same on GitHub, but you know what? I can save this file and I put it on GitHub, right? Okay? So then